Right, actually, before you. Exactly. We'll start recording.
Well, thanks. Hi, everyone. As Ian said, I'm Alexandra. I appreciate you all having me today to talk about two projects I've been working on over the past few years in characterizing local environments of fast radio burst using high resolution imaging of the host galaxies. So I guess I just want to start off by kind of motivating the work that I'll be talking about today. The first main motivation is thinking about fast radio burst origins. So progenitors, what is producing them, where are they coming from, and doing so through host galaxy studies using high resolution deep imaging from Hubble Space Telescope, or HST, which allows us to investigate different progenitor channels through characterizing the local environment around the FRB, or from where the FRBs are originating. And then the second motivation is magnetic field characterization, or using FRBs as tools and as probes of the universe. And so characterizing the magnetic field properties by looking at FRB polarization and rotation measures, and how those kind of fit into the story that we're telling with the kind of global properties of the host, or the kiloparsec scale environments that we're looking into in the first project. So just a little outline. I'll first go through a brief introduction to transients in general and FRBs more specifically. And then we'll look at the first project about dissecting the local environment with high resolution imaging. So where we present our HST images. And then lastly, we'll finish looking at the FRB rotation measures as probes of galactic magnetic fields. So what are transients? They are events that happen and evolve on kind of human time scales, ranging from, fractions of a second to years, something that humans in our lifetime can watch change and watch evolve. And these can be things like supernovae or merger events or gamma ray bursts, things that also might have other accompanying transient events happening in other wavelengths. And we can use all of these observations to understand better the physics of compact objects, so black holes, stars, things like this. And one of the key things to kind of uncovering the origins of I guess specifically long duration gamma ray bursts in this case, was using high resolution imaging from HST to understand the progenitors. And one thing that this paper did, Fruchter et al. 2006, was taking HST imaging of long duration gamma ray bursts and core collapse supernovae hosts and comparing them to one another. Because we have a pretty good understanding of core collapse supernovae, what types of stars result in a core collapse supernova. But at the time, we were not, or the field people, the authors of this paper, weren't necessarily sure about what was creating long duration gamma ray bursts. And so in these images on the left is the hosts of long duration gamma ray bursts. Many are irregular, have irregular morphologies. And then with the core collapse supernovae hosts, you see massive like spiral arm or spiral galaxies. And then taking a closer look at the location of the transient events, especially in relation to the distribution of light throughout the hosts, that the long duration gamma ray burst events were happening and concentrated in the brightest regions of the galaxies, whereas core collapse supernovae, these explosions were distributed across different brightness levels. So some were occurring in the brightest regions of the host, and others in very dim regions. So all these different puzzle pieces fit together to form this larger picture of the long duration gamma ray burst origins through characterizing the light at the location of the burst, studying global host properties like the metallicity, star formation rate, stellar mass, also looking at the morphologies of the host made possible by the HST imaging. And also a key is comparing to other transients, looking at things that we have a more clear or better understanding of their origins and the physics of their creation, and how do the sort of unknown transient events compare to that. And putting all these pieces together to finally come to the conclusion, in this case, that the long duration gamma ray bursts were originating from a special class of supernova. So this is where the new mystery enters the scene, which is FRBs. And the big question, why are they interesting? What makes FRBs so interesting? And that is they kind of exist in this very unique area of this, phase space of luminosity and duration. They're very high luminosity, very short duration on like millisecond time scales, and some even repeat. And in the FRB signal itself, there's a lot of information embedded in it. You have the dispersion measure, which quantifies the amount of ionized material that the signal traveled through on its way to us, which results in this delay in different frequencies arriving to the telescope and detectors, and how big that delay is can tell you about the density of that material. And then you also have the rotation measure of FRBs, which can tell our polarization signals of the FRB that tells you about the kind of magneto-ionic environment around the FRB progenitor itself and magnetic fields along the line of sight. And so again, the question of what are their origins and what tools do we need in order to solve this question? And one thing is localizations. We need to know, what host the FRB is coming from, what galaxy can we associate it to in order to get more information about its origins. And FRB localizations have come a long way. We've gone from, localizations on the scale of arc minutes, where there are many or a number of possible hosts within that localization region that we can make some sort of, statistical statement about where it might come from, but we can't make very secure associations with localizations on that scale. To then sub-arc second localizations, the first being 2012-1102, where we can then see exactly where in the host the burst is coming from. Is it associated, with other sources, or in this case, like a persistent radio source in the host, and what's the mass of the host? In this case, for 2012-1102, it was this star-forming dwarf galaxy, which kind of started to then make us ask the question, okay, well, what are other FRB hosts like? And are they all star-forming dwarf galaxies? Do they all fall into this very particular category? And so the CRACO experiment, in the case of this project, helped us to start to answer that question, as they were producing high precision localizations that allowed us to make kind of high confidence associations with host galaxies. So they use the ASCAP telescope. CRAFT is for commensal real-time, ASCAP fast transient survey. And so at this point, this says about 25, I think it might even be more around 30 or so high precision localizations in papers like Bhandari et al. 2020. They can do this follow-up and ground-based imaging of the hosts of these events. and start to make measurements on, stellar mass, star formation, metallicity, all of this kind of stuff. Same in Hines et al. 2020. And then looking at the whole population, and in comparison to the host of 121102, you can see that a lot of the hosts differ markedly from the host of 121102. There are some that are similar, also kind of dwarf star-forming galaxies, but many of them appear to be massive star-forming galaxies. Also, a number show spiral structure and things like that. So does this point to the possibility of different origins, different kinds of progenitors that are making bursts like 121102 versus other bursts? And one way that we can start to learn more about that and answer that question is by utilizing Hubble and its capabilities. And so what it can help us with is looking more closely at whether or not the bursts are coming from regions of enhanced star formation or stellar mass. We can start to detect and resolve lower surface brightness features in the hosts. In this picture on the left, there's like a hint of spiral arms, maybe out in the distance at higher radii, but in these ground-based images, we're not quite able to resolve and detect that. So that is another thing that HST can really provide. And then another thing is deep imaging that can help us place constraints on whether or not there is like a faint host that is the true origin of the FRB. Is there some satellite or background galaxy at the location of the FRB that is its actual host? And so HST can help us place constraints onto whether or not we think that may be the case. So for our sample selection, we wanted sub-arcsecond localization and a secure host association. 6 of the hosts in the sample were newly imaged and presented in Shatidi et al. 2020 and Mannings et al. 2021. And then 2 previously imaged hosts, that's 2012-1102 and 1809-16, for a total of 8 hosts in this sample. And here are some of the images that we took. The first up at the top is FRB 1906-08. We have UV and near-infrared images for all of the hosts in the sample. UV to probe like star formation and massive star populations, whereas the near-infrared helps us to look at stellar mass and morphology, things like this. And you can see that the other one is 1910-01, as the title says. So here are all of the hosts. This is the near-infrared images for all the hosts in the sample. The R designates it's a repeater, and the NR means non-repeater. So 3 out of the 8 are repeating, and then the other 5 are not. So some of the measurements that we make using this data, we look at morphologies, we measure the radius of the host, we look for any residual kind of structure in the images, things like this. I'll talk more about that in a moment. We also measure the galactocentric offset, so how far is the FRB from the center of the galaxy. We look at stellar mass and star formation, surface densities at the FRB location. We place luminosity limits on that possible faint host that I mentioned earlier. And then we also look at the fraction of enclosed light, which I'll talk more about in a moment and explain what that is. So first, starting with morphology, we use GalFit to fit 2 models to the near-infrared light, one bulge component and one to the disk. And then we subtract off these models to identify any underlying substructure. And when we do that for 1906-08, we were already able to see, the spiral arms kind of well in this image, but once we subtract off those models, they really pop out at us. And we also use this to derive the half-light radius of each of the hosts. And so when we look at all of the hosts in the sample, we see a spiral structure show up in 5 out of the 8 hosts. And not only that, but the FRBs in these hosts are landing on or very near to the spiral arms. So that was an exciting find. Then we can also place the luminosity limit on the faint galaxy. So using that residual image, subtracting off as much light as we can at the FRB position, we place like a magnitude limit on what does the luminosity of this background galaxy have to be in order for us to not see it at this point. And then using that, looking at what the redshift of that galaxy would then have to be in order for that to be the case. And so we use the luminosity of the FRB 121102 host as a kind of benchmark to compare against. So I'll bring these up so we can see. So the upside down triangles, or the triangles, are the limit placed on a satellite host at the same redshift as our putative host. And many of these, all of them, would have a significantly lower mass and therefore luminosity than the host of 121102. All of these triangles, are well below that purple line. And then using the kind of error on the dispersion measure, we can say, well, if we push to the highest end allowed by that dispersion measure and what that kind of upper limit on the redshift could be, then what luminosity would a host be at this higher redshift? And there are 2 hosts that meet or exceed the luminosity of 121102, but again, most of them, even at the higher redshift background galaxy, the luminosity would be significantly lower than the luminosity of 121102. So we use this to kind of say we think it's unlikely that the FRB originates from a satellite or a background galaxy that isn't already apparent in the images. So strengthening our association to the host that we thought it was, this putative host. Then we do a statistical analysis on a number of the measurements that we made. We compute cumulative distribution functions, or CDFs, of these different measures, like offset, a measure called fractional flux, which was one of the key measures in the Fruchter et al. 2006 paper, and then also this fraction of enclosed light measurement. And we employ a KS test against FRBs and these other transient populations listed below to test whether or not they come from the same underlying population. So I'll just show, and this again helps us to test against, well, if they're coming from the same underlying population, maybe they are produced by the same type of object or progenitor or event, things like this. So taking a look first at offset, looking at the distance between the FRB and the center of the galaxy. We use like a 2D Gaussian distribution, like probability distribution within the offset or the localization region in order to compute the offset with some probability. And looking at the projected offsets, the black line shows the FRBs, other transient populations shown in the different colors. Our median projected offset is about 3.2 kiloparsecs. And with this test, we reject association with long duration gamma ray bursts or superluminous supernovae. These are occurring at too low of offsets, too close to the long duration gamma ray burst. Yeah, they're both occurring too close to the centers of their galaxies. FRBs are at a bit higher offsets. And then we normalize with the size of the host. So the host normalized offset, now we're not just saying, okay, well, 1 kiloparsec offset can mean very different things in a small versus a larger galaxy. So we're normalizing across all of these host sizes. And with this KS test, we reject FRBs originating from the same underlying population as calcium-rich transients. And here the median is about 0.9 effective radii. Then we came up with this measurement fraction of enclosed light. So at the offset of the FRB from the center of the galaxy, you kind of draw a circle, or we used isopotes and said, okay, within this isopote, how much of the galaxy's total light is within the radius of the FRB, or within the offset of the FRB. And for this, I'm showing the example of 1906-08 again, and about 80% of the host light is enclosed within the radius where this FRB is occurring. And this lets us kind of probe the light at the location of the FRB with respect to like the radial distribution of the light in the host, taking into account the morphology of the FRB host. And this is in contrast to a measurement like fractional flux, which is like morphology independent. And what we find here is that the distribution of FRBs is consistent with the radial distribution of stellar mass. So it's tracing it fairly well. And then we look at derived local properties. So this is us computing the star formation and stellar mass surface densities at the FRB location. Again, showing 1906-08 as our example. And for 1906-08, we're landing really close to this star forming knot, which stands out a lot in comparison to the rest of the host. But what we find in general is that the local stellar mass surface density is often very similar to the global value. So it's tracking that one-to-one line. They aren't occurring in regions of particularly elevated stellar mass. And this is also the case with the star formation surface density as well. In the case of 121102, it does occur in this region of very elevated star formation, but that exists in contrast, I think, to what we see for many of the other hosts in the sample. And yeah, not only that, but we were only really able to place upper limits on many for this measurement for many of the hosts. But even then, those upper limits were very close to or even below that one-to-one line. So again, not really regions of particularly elevated stellar mass or star formation. So the key takeaways from this are that it is unlikely that a faint satellite or background galaxy is the true host of these FRBs. We feel really secure in their association to the hosts that we have imaged and studied in this project. Also, we see spiral structure in a lot of the hosts and more than half of the hosts in the sample. And when we are seeing this spiral structure, these FRBs are on or very near to the spiral arms and kind of consistently at pretty moderate galactocentric offsets. And we're also seeing that the FRBs in this sample trace the stellar mass, and we're not in regions of elevated star formation or stellar mass. And the implications of this we don't find very strong support for a connection to the most massive stars or events that require kicks and long delay times. So no, neutron star mergers happening all the way out at the ends of the disk. But it also does not rule out magnetars as progenitors in general. There are other ways to make a magnetar, but it also then can tell us that there is a possibility of multiple progenitor channels. I don't think the sample was quite big enough to make really confident distinctions or differentiations between, repeaters and non-repeaters. Some of the repeaters in this sample even showed very similar characteristics to the non-repeaters. But yeah, it seems that there are possibly a number of ways that you can create FRBs that would account for these differences in host characteristics and all of that. So now let's use some of our knowledge and measurements from this study to think about galactic magnetic fields. And this takes us into our rotation measure study. So generally, measuring magnetic fields is pretty challenging. There are a number of ways that we can or people try to do this. There's the Zeeman effect, which causes splitting in your line splitting in your spectra. You've also got synchrotron emission. There's also the polarization of light, and that's what we're going to focus on today with rotation measure. So with polarization, that just means that the direction of the oscillations in your electric field are well defined, and FRBs are generally polarized emission. And the Faraday effect is when you have this linearly polarized light or signal, a magnetic field can change that angle of polarization. It can cause it to rotate, and the magnitude of that magnetic field and the density of this ionized material can affect how much it rotates. And so we can measure this, angle of rotation to get our rotation measure, and then use that to define or constrain the strength of the magnetic field that the signal, traveled through in order as it was on its way to us. And this is just probing the component of the magnetic field that is parallel to the line of sight. There are other methods to probe other components of the magnetic field, but the rotation measure tells us that which is parallel. And so we can learn about galactic magnetic fields, Faraday rotation, and therefore the magnetic field magnitude at the FRB location, which is very exciting. But then also, it has to interact with material and magnetic fields on its way out of the host, so we can get more of a picture, not only about the local environment, but we can say something about the host itself as well. And one tool that we can use in this process is galaxy simulations that look at the production and amplification of magnetic fields in galaxy formation and evolution, and how these are in relation to each other. And looking at these simulated galaxy Faraday rotation maps and seeing, okay, well, these synthetic or simulated values, how do they compare to what we're actually measuring through these host galaxies? And these are hosts from the Auriga project. There's 3 different hosts chosen, showing rotation measure values in different colors. The brown is like a more negative rotation measures, with the blue being very positive rotation measures. And we can make very, informative comparisons for the simulators themselves to say, okay, you're doing a good job. And also to say, if they do match, what kind of physics does that implicate, and what are we probing when we're measuring the rotation measure of the rotation measure of the FRB and all of that. So our main goal is to infer magnitudes of galactic magnetic fields. And the 3 questions that we're asking and trying to answer: what are the typical magnetic field strengths indicated by the FRB rotation measures? And do we see trends with magnetic field strength and other galaxy characteristics? And lastly, how do the rotation measures of quote unquote normal galaxies compare to those predicted by the magnetohydrodynamic simulations? So first we characterize our sample. It's mostly represented by star-forming galaxies, two of which are quiescent and another two maybe transitioning over, and then mostly existing between kind of that blue cloud and the green valley. And then we see a very low, I guess, contribution from the intergalactic magnetic field to the rotation measure that we see, and that it's mostly due to the host contribution. In the case of dispersion measure, we see a very strong relationship between dispersion measure and redshift. As we go to higher redshift, we see higher dispersion measure values. Whereas for rotation measure, there was not much of a Z dependence that we saw as we went to these higher redshifts. Yeah, there wasn't much to see. And I think this caused us to, well, this along with some other piece of information, such as like measurements of the RM excess or magnetic field strengths in filaments being pretty close to zero, very low. This caused us to treat the contribution from the intergalactic medium as negligible. And when we search for correlations between these other characteristics and the rotation measure, we found a very strong correlation between DM host and RM host, as well as host normalized offset and RM host. So this is showing a radar plot. The radius are the R values from the Spearman correlation test, and then the values, the PS values are, quantifying the kind of confidence in that correlation. And then the host normalized offset has just an outline of a star around it, because that is an anti-correlation. And we find weaker correlations between RM host and the overall global stellar mass and the star formation surface density. And so taking a closer look at DM host and the host normalized offset, you can see pretty strong correlation between RM host and DM host, as well as the offset. One thing I guess to note in this case is that we determined our DM host value using the McCourt relation. So estimating the cosmic contribution to the dispersion measure, subtracting off the estimate from NE 2001, and then what we're left over with is our DM host. And so there is a bit of error to account for there. But I think even still, it's a pretty good indication of some sort of correlation between the two. And then also, I thought the correlation between the host normalized offset and RM host was interesting. So as you're going out to higher radii, you're getting to lower and lower rotation measures, maybe as you're going through less ionized material, interacting with weaker field strengths as you're going out to higher radii. And we're also able to, this is one of the equations from Akahori et al. 2006 that talk about kind of getting the magnetic field strength from the ratio between the rotation and dispersion measures. And so we plot here the rotation and dispersion measures for each of the FRBs in our hosts, and then there are lines of constant magnetic field, so we can kind of compare to see where most of these points lie. And we see that many of them are below 5 microGauss, and even then many of them are below the 1 microGauss line. So relatively, I guess, low-ish field strengths if you're comparing to the local solar neighborhood, for example, which has a value around 6 microGauss. but this is still consistent with micro-Gauss, what's the word I'm looking for? Magnitude fields that we expect from galaxies anyway. So this felt pretty good. And then we also look for any sort of, I guess, relationship between magnetic field strength and the stellar mass and star formation rates in the host. And also we wanted to just compare, here we compare against the Milky Way as a benchmark once again, to see that many of these points lie below the B field magnitude of the Milky Way measurements. And then the orange is showing the inner magnetic field of the Milky Way, and the yellow is the outer magnetic field of the Milky Way. But I think a number of things could contribute to this. One is that we're only probing one component of the magnetic field strength. This doesn't take into account, the perpendicular field and other field components that could contribute to the overall strength of the magnetic field. So, but I think still informs us of something nonetheless. And finally, our comparisons to simulations. So here on the left, just showing a strong correlation between the dispersion and rotation measures, the synthetic dispersion and rotation measures from the simulations. And then, I guess to reiterate, we're comparing to the Auriga project simulations, which are magneto-hydrodynamic cosmological zoom simulations. So we're able to pick out hosts that are similar in characteristics to the hosts in our sample with respect to stellar mass and star formation rate and other characteristics, and then make comparisons for what rotation measures, or in this case, a distribution of rotation measures that you get from, selecting a bunch of different sight lines through the host galaxy. So the curves in the plot on the right, yes, the purple curve is the rotation measure distribution, and then the purple vertical line is the measured value. And then the pinkish reddish curve is the dispersion measure distribution, with that pinkish reddish vertical line being the measured value. And what we find is that the simulations predict the rotation measures reasonably well. We do, just as a test, place a constraint on sight lines that have a dispersion measure less than 2 times the observed dispersion measure, and that is the rotation measure distribution that is shown with the dashed yellow line. And again, still pretty good agreement between the simulations and these measured values. One thing, though, to think about, I guess, is as we find good agreement between the two, between the simulations and the observations, is if there is any sort of like excess in the observed rotation measure, can we use that to I guess think more about what the local environment is like? Is there sort of enhanced magneto-ionic environment around the progenitor or around the source that is causing it to have some RM in excess of what is being predicted by the simulations, which should just take into account the ISM and the halo. So I think that kind of promises some exciting things to look into in the future. So some of the key takeaways from this, that we found magnetic field strengths that were consistent with this micro-Gauss magnitude magnetic field strengths that we expect generally from galactic magnetic fields. We also see these strong correlations between RM host and DM host and host normalized offset, which I think highlights the effect of the host environment on the rotation measure itself. And then we also see that we can use comparisons between observations and simulations. One, to constrain the simulations and what they're doing with the physics in there, but also to learn more about these galactic magnetic fields and progenitor environments of FRBs. So yes, we can use FRBs to probe galactic magnetic fields. People said it before and have tried it before, and just, supporting that statement and claim. We can also use the rotation measure, as we've seen before, to learn about the magneto-ionic environment around the progenitor, and the comparisons with simulations can be a really helpful tool in that. And then also we see that RM is strongly correlated with the dispersion measure contribution from the host, but there is not as strong of a Z dependence with RM as there is with dispersion measure. So through various, effects from field reversals and things like this in the intergalactic magnetic field, that the contribution from the intergalactic medium is not really as high as what we see with dispersion measure. And that's it. Thank you.
Thank you very much. That was a super interesting and clear talk. Please just raise your hand if you have any questions. Go ahead.
Very nice talk. So a quick question is, like, when you say comparing the magnetic field distribution with the simulation, actually I find it slightly surprising it's consistent, because like the normal pulsar line in the high galactic pulsars are not having that many high RM cases. So I'm just curious, how do you compare those? Like, how do you choose the line of sight, or how do you compare it also? Like, because in the plot you're comparing the RM over DM, so you're not directly compare the distribution of RM and distribution of DM, but you're sort of comparing some distribution of the combination. Direct.
Yeah, so we're comparing like a distribution determined by, I think it was like 256 sight lines through the simulated galaxy to the measured rotation measure of the individual FRB. Yeah. And the sight lines were chosen to be like, I think, not very young stars, but also not very old sources either, kind of with an age somewhere in the middle. And we also, I think, tried to avoid like very dense H1 regions. So that was those are most of the constraints on the sightline selection. So can you
I was just thinking, like, so the RM has a distribution and a DM has a distribution, and the RM with a variance over DM with a variance, and it's sort of getting very complicated. So if you just directly do the RM distribution and DM distribution compared to the simulation, is the RM distribution consistent with the prediction from the simulation?
We have mostly we really just compare the distribution from the simulation to the single kind of accepted value for the rotation measure. We didn't compare the two distributions to each other, but that's a
okay, thank you.
I'll think about that. Yeah.
Casey?
Thanks. Yeah, Alex, it's great to see this work coming together. I don't know if you remember, we met a few years back in Santa Cruz. Yeah, it's really fantastic to see the results coming out from your work. I just wondered if you had any thoughts on repeaters and non-repeaters. There's certainly radio properties that are different, but in terms of hosts, anything stand out to you in your analysis that makes one look distinct from another?
Yeah. I guess there was like 121102 and the host of 190711 were both these like star forming dwarf galaxies. But then you had 180916 that was a star forming spiral galaxy. You also have like 20201124 that is again this star forming, looks like at least a disky galaxy. And so I think there was a little bit of wanting to draw a line between the repeaters and non-repeaters, but it seemed like a lot of the hosts of the repeaters were pretty similar in characteristics to the non-repeating hosts as well. But I think right then, once we started looking at the rotation measure information, then there was a lot of stuff going on there with like variations in the rotation measure between the different bursts and all of this kind of stuff. So there was a lot of new information, I think, as we started to look into that. But even then, I think a lot of the correlations, the only outlier was really 121102, not many of the other repeaters in the sample as well. But I think, yeah, I would love to have a much larger sample to really try to disentangle the two.
Right. Yeah, it may well be. I mean, it's natural to imagine that the radio properties will tell us that classification, if there is such a thing, prior to the host galaxies. But it'd be really cool if there's a way to support it with the host galaxies, but maybe it's just too obscured. Yeah, thank you.
Mm-hmm.
I have a quick question. Yeah, go ahead. So that was a great talk, by the way. So you mentioned quickly that the excess, if you're seeing excess R in comparison to the Eureka simulations, then it might be indicative of like a might be a dynamic ionic environment with with respect to the host or the local like source rather than the host, or something along those lines. And there are a lot of progenitor theories out there, but a lot of them sort of entail like really high magnetic field environments for the local source, like magnetar, emission theories and things like that. And so I was wondering how you sort of reconcile the fact that like most of the magnetic fields you're getting are still on the order of the host galaxy rather than about like say 10 to 12 to 13 that might be expected from like a high magnetic field host or something.
Mm-hmm. Yeah, that's a good question. I guess, yeah, I guess in some cases, like you have the 121102, right, that has an extremely high rotation measure, and we see that that excess when we compare to the simulations, and it's like, oh well, okay, we know what's more so what's going on in that case and can come up with an explanation of it. But yeah, when they're in agreement, I'm not sure. I guess that just means, it's coming from something that has a little less, like a little lower magnetic field strength at the source, but yeah, that's a good question. But I guess I should also say again, like we're able to probe one particular component of the magnetic field, and that maybe follow-up of other kinds of indirect ways of measuring the magnetic field at the source or at the location might also be interesting to look at, to see if maybe we're not getting the whole picture just looking at rotation measure or things like that. But I'm not sure. That's a good question, and I will think more about that, about what it means for the kinds of sources that might then cause us to make measurements that are on the order of or really similar to the galactic magnitudes.
Yeah, thank you. It was just something I was curious about. But there are like a lot of there are a lot of gender theories out there, and also you have things like field switching and stuff like that could affect it too. So it's probably more complex than like I'm thinking about. But yeah, thank you.
Yeah.
I have a quick follow-up question on that, actually. So in the, in your observations, if you account for inclination angle, then I guess there wouldn't really be a correlation between Rm and Dm if, unless the, Rn and Dm were coming from quite local to the source. So presumably this correlation just comes from the fact that you're traversing more ISM. So did you attempt to model inclination angle of these host galaxies?
We did account for inclination angle. Yes. I didn't really understand the second part of the question.
Well, I guess my point is just that if the Rn and the Dm were really local to the source, and they were correlated because it was the same magnetoionic plasma, then there shouldn't be any dependence on inclination angle. So if you're looking at the galaxy edge on, it doesn't actually give you all that much more, but much more Rm or Dm because it's all local anyway.
I see.
Now in this simulation, the figure on the left here, is that's just because you are probing different lines of sight in the galaxy that include through the disk and out of plane.
Yeah. Yeah.
Yeah, so unrelated question is like in the first few slides when you were saying that the offset study is like rejecting the long time delay model. And I just want to know more quantitatively, what is the current upper limit of the time delay?
I guess nothing, well, what is I think it's like on order of magnitude 10 to the 6 or something like this, but I need to look more into that to give you an accurate answer. Yeah.
Okay, thank you.
Any more questions?
I have one other question. So in a couple of your plots, you were comparing those properties of most of your sample to say 12.102, which seem to disagree in most cases or be an outlier in most cases with like DM and the star function rates, things like that. But a lot of like for some literature has suggested that it's more that it's like a different progenitor or different type of progenitor, I guess. I was wondering if through your analysis you had an opinion on whether or not the differences in the 12.102 are more due to the host or due to the progenitor, or either.
Sorry, I couldn't quite hear.
Sorry, yeah, let me come a little closer to the mic. Yeah, so I was more just wondering, 12.1102 seems to be sort of an outlier in a lot of studies, including this analysis. And I was wondering, since this is mostly comparing to host properties, did you have an opinion on whether it seems like the differences are specifically due to the host, or maybe more due to more to the source environment, or the source itself?
I guess that's an interesting point. So in the rotation measure study, I think most of the galaxies were, again, star forming with either like disk or spiral structure or something like this, with maybe, I think, one or two not fitting that description. Let's see. And yeah, when 12.1102, it's an outlier in both regards, the FRB like properties, specifically the rotation measure, and also the host properties. And the others, I guess, seem to still be correlated, even when not taking into account 12.1102. I'm not sure that answers your question.
Oh, no,
So maybe need to think more about it, yeah.
yeah, it's probably not like a straightforward answer, right? Because this is, I think, popped up in other, previous papers as well, where 12.2 just kind of seems like a weird outlier. But it seems like an FRB, of course, but it seems like an outlier, so I think it's probably a more detailed question than I'll give it credit for it. But yeah, it's just interesting to see it reflected in your work as well. Yeah. Thank you.
Okay, with that, I'll thank Alexandra again on behalf of everyone else.